Tired of waiting for colonization? Does the Earth seem way too boring with all its problems and mosquitoes? Well, have no fear. It's time to take matters into your own hands and build your own planet. But before you start reaching for the cosmic glue and glitter, there are a few things you'll need to consider. Let's start our ultimate DIY project. First of all, we need to choose a location. Every planet has to orbit a star, right? In a cosmic buffet, every star has its own unique flavor. To keep things organized, astronomers use the so-called stellar classification system. The massive stars are the divas of the cosmos. They're huge, bright, and are always stealing the spotlight. But it's not all sunshine and rainbows. They have a short lifespan, burning out super fast, like a candle. They also have huge gravity, so be careful that your planet doesn't get sucked in. The dwarf stars, on the other hand, may be small, but they make up for it with their stamina. They can burn for trillions of years, which means that their planets have plenty of time to develop life. Super hot stars are blue or white ones, while the cold stars are usually red or orange. Yeah, seems like it should be the other way around, but we're not the ones making the rules. So what do we choose? Well, the planets around the blue and white stars could be scorched and fried, like a crispy chicken nugget. On the other hand, with cool red stars, our planet may turn into an ice ball. If that's your preference, then sure, but you can always pick a nice middle ground. A yellow star like our sun, for example. Not too cold, not too hot, but just right. Now that you've picked the star, let's start building the planet. The heart of the planet is its core. The core creates a magnetic field, an invisible force that protects a planet from harsh cosmic rays and charged particles. If it weren't for this field, the planet would be fried by the star's radiation, like a well-done burger. But the magnetic field isn't always a force for good. On some planets, like Jupiter, it's so strong that it creates super intense radiation belts and some crazy weather. If you were hoping to use a compass to find your way around on such a planet, forget it. The magnetic field would have the needles spinning like a breakdancer on caffeine. So, if you pick a small light core, the planet will have less protection from solar radiation, like tanning without sunscreen. On the other hand, larger cores can generate more heat, which can lead to more volcanic activity and earthquakes. The best option is a medium-sized core made mostly of iron and nickel. Enough to keep the bad things away, but not too strong to turn a planet into a cosmic hot potato. Once the heart is in place, we can move on to the next step. Planets are like onions. They have layers. Most planets have three main layers: the core, the crust, and the mantle. The core is the filling, as we've already discussed. The mantle is like a hot and gooey layer of caramel between the crust and the core. And the crust is like a thin layer of icing on a planetary cake, covering its surface. But not all planets are built the same way. Because of that, we have tons of options. First up, we have the gas giants, the big boys of the universe. In our solar system, it's Jupiter and Saturn. They don't have a crust at all. They're basically huge balls of gas, like hydrogen and helium, hence the name. Next, we have the ice giants, like Uranus and Neptune. They're like younger, cooler siblings of gas giants. These planets don't really have a solid surface, but it's not pure gas either. They're made mostly of water, ammonia, and methane ice. There are also ocean worlds, and no, they aren't made of pure water. They do have some kind of solid surface, but it's located so deep, and the ocean on their surface is so huge that it kinda does look like a giant water drop. Finally, we have terrestrial planets, like the Earth. They're made mostly of rock and metal. These planets have a surface to stand on, and usually come with a cool mineral collection. And let's not forget about the dwarf planets, the small but mighty. Pluto is probably the most famous one, but there are others in our solar system. Eris, Charis, Haumea, and so on. They're the scrappy underdogs of the planetary world, always trying to prove their worth, but never making it to full-fledged planets. Which type do you like the most? Gas giants are probably the coolest ones with their enormous sizes, crazy winds, and scary lightning. We also need to create an atmosphere. It's the outer layer of a planet that plays a huge role in its climate and weather. It's also the planet's ultimate protector. Did you know that 90–95% of meteors burn up in the Earth's atmosphere? Imagine what would happen if they didn't. Dense and hazy atmospheres, the ones you'll find on places like Venus, have thick layers of carbon dioxide and sulfuric acid. In other words, it's not a planet, but an oven. It's so hot that you could cook a pizza on its surface in no time, and get cooked yourself. Next, we have thin and wispy atmospheres, like on Mars. The thin layer of carbon dioxide makes its surface pressure about 1% that of Earth's. On planets like these, you could fly like a superhero if you had a good enough jetpack. Then we have mixed atmospheres, like the one on Earth. The layers of nitrogen, oxygen, and other gases create the perfect conditions for life as we know it. It's also where we get to enjoy sunny days, rainbows, and, of course, water. And last but not least, exotic atmospheres. You'll find them on planets like Neptune, where the layers of hydrogen, helium, and methane create a blue-colored world that looks like a giant marble. They're super weird and unusual, so just perfect for creative planet builders. Almost done! The final question is, would you like your planet to have life on it? In that case, there are some things you should consider. For example, it should be located in the habitable zone. This is the sweet spot around a star where conditions are just right for liquid water to exist on the surface. Make sure your planet isn't too close or too far from its star. And don't forget about the temperatures. For example, you'll want a good amount of oxygen for a planet to be nice and warm, but not too much that everything spontaneously combusts. Of course, we need some water, but not too much, and a stable climate. You don't want your planet to be going through extreme swings in temperature or moisture. That's a recipe for extinction, not evolution. Oh, and the orbit should be stable, so that there are no major astronomical events that could throw things off. As you can see, this type of planet is very picky. No wonder it's so hard to find extraterrestrial life. Anyway, now that we've finished messing around in the planet creation editor, how do we even build it? Well, how about terraforming? It's when we deliberately alter a planet's atmosphere, temperature, and other conditions to make it habitable for humans and other Earth-based life forms. For example, we could release greenhouse gases on Mars to warm up the planet and create a thicker atmosphere. But this method is more like polishing a monstrosity that was given to you by a character randomizer. What about building from scratch? That's something straight out of sci-fi. But maybe in the future, we could do that using large-scale 3D printing or nanotechnology. We could create the basic structure and then add all the necessary conditions for life to exist. Of course, all this is still purely theoretical, but while creating a planet artificially is still a long way off, there are many creative ideas and concepts being explored by scientists and sci-fi writers. Who knows what the future might hold for the possibility of creating new worlds? There's a chance that our entire Milky Way galaxy is located in the so-called space void. It's a region where there's relatively little matter as compared to other corners of the known universe, and it's much less dense than it is elsewhere in the universe. In other words, we might exist in an air bubble in a cake. If that's true, it would mean that we're even lonelier than we thought. In our universe, all the galaxies are constantly moving away from each other. In order to understand how far they move away, scientists use something called the Hubble-Lemaître constant. It's like a speedometer, but for galaxies. However, there's a cosmic mystery called the Hubble tension. It's challenging what we know about the universe's expansion. Scientists used to consider the Hubble emitter constant a reliable guide, but our recent observations question this reliability. The speeds we see in real life don't match up with the distances we calculated and expected. They aren't sure why these measurements don't add up. Researchers followed the moves of supernovas and saw that the universe seems to expand faster around us than it does overall, as if it's actively avoiding us specifically. After considering this, they began to assume that we all might live in a cosmic void. Cosmic voids are vast, empty spaces between galaxies. They make our entire world look like a big sponge. Let's go back to the beginning, just a fraction of a second after the Big Bang. Right after the beginning of everything, the universe was a hot, compressed plasma. It only had very tiny variations in density called quantum fluctuations. After the Big Bang, the universe began to expand. Those quantum fluctuations grew together with it, creating regions of varying matter density. Because of that, the universe didn't expand everywhere uniformly. Instead, little claps of matter began to gather together over a long time, creating massive structures. Galaxies. Galaxies are arranged in huge walls and filaments with enormous gaps in between. And these gaps are the voids, also known as dark space. These voids aren't truly empty. In fact, they actually hold more than 15% of the amount of matter found on average throughout the entire universe. They still contain gas, dust, dark matter, and even stars and galaxies. However, they have less density than regions with galaxies, about a tenth of the average matter density, which is why we consider them nearly empty. Usually they have a diameter ranging from about 30 to 300 million light years. That is an enormous distance, even on a space scale. For comparison, most planets and nebulas we've found so far have a distance of hundreds and rarely thousands light years away from us. In the case of voids, if you were in the middle of one, it would just look like seemingly eternal darkness. The closest stars would be so far away that they would be almost invisible to you. Some of them are especially large. They're known as supervoids. The largest known one was creatively named Giant Void. It's so big, it's impossible for us to even imagine. 1.5 billion light years away, with a diameter of 1 to 1.3 billion light years. Yes, it's basically a giant dark vacuum, but even this giant vacuum isn't entirely empty. The giant void houses 17 separate galaxy clusters within its expanse. However, it might not be the biggest emptiness in our world. There's this thing called the CMB cold spot. It's this unusually large and chilly area of our universe that we saw through the microwaves. It really stood out on the map of our universe with its unexpectedly low temperatures, and scientists have spent many years trying to figure out what this thing is. In 2015, scientists proposed that this place might be a supervoid, and probably the largest one ever. Being even more original with this one, they called it the Great Void. If it's true, this place would be an emptiness about 1.8 billion light years in diameter, about 1,000 times larger than typical voids. Not everyone thinks that it's possible, so scientists keep arguing over this one for a while. There's another interesting theory going about this place. One researcher suggested that this place might have been a trace from our collision with a parallel world. It's a pretty bold hypothesis, but unfortunately, there's no way for us to confirm or deny it with our current technologies. In any case, as the universe expands, these voids will grow, and the walls connecting galaxy clusters will stretch and break. Eventually, the voids will merge, leaving gravitationally bound galaxy clusters as islands in the expanding emptiness. In other words, sooner or later, the great emptiness will consume everything in our world. So, it turns out, we might be a rare occasion in a supervoid, one of the 15% of matter. This would explain why we're surrounded by relatively few galaxies. This discovery, if true, challenges the standard model of cosmology which we created with Albert Einstein's help. It would mean that gravity in general behaves differently than what we expected. According to the standard model, such a significant underdensity shouldn't exist. Because of that, scientists will have to explore and consider this idea thoroughly. It might just challenge our very basic understanding of physics. The scientists called this the local hole. The discovery of the local hole may hold clues to explaining the Fermi paradox. Maybe in the specific part of the universe where we hang out, the chance of intelligent life developing anywhere nearby is very low. Perhaps all the sentient beings hang out somewhere beyond our super void. But that doesn't mean that we should lose hope, or that life anywhere nearby is impossible. In fact, life in the universe might be much more common than we previously thought. We know that the inner planets, like Mercury and Venus, are inhospitable due to extreme conditions. However, Venus looks interesting because, even though it's a crazy toxic planet, scientists believe that it was very Earth-like in the past. It could have even hosted life. Unfortunately, it was too close to the sun, and all the nice conditions evaporated over time. But there's a possibility of microbial life surviving in its high-altitude clouds. Mars, a cold desert, also might have been a friendlier place in the past with rivers and lakes. Though now it lacks a protective atmosphere, ancient life might have existed there. In that case, it would leave potential fossils, and underground microbes could still survive. We've discovered some signs of them, but are still debating whether this stuff was truly organic or not. The gas giants, like Jupiter and Saturn, and ice giants are not ideal for life, but their moons offer hope. Europa has an ocean beneath its icy surface, making it a potential hotspot. Enceladus releases water into space, carrying complex molecules that hint at interesting possibilities. And Titan is especially unique. It has liquid bodies on its surface, rivers and lakes of hydrocarbons. While its frigid temperatures aren't great for life, scientists ponder if it might host life with a different kind of chemistry. However, it will take us decades to check all these celestial bodies and study them properly. We haven't sent anything so far since the times of Voyager 2, but if we're lucky, we might explore our solar system during the 21st century. In any case, there's a lot of potential for life, even in our solar system alone, not even mentioning all the planets and galaxies we've found nearby. Our estimates suggest that the observable universe, the one we can see, might host around 5.3 trillion habitable worlds. One of the most likely candidates so far is Kepler 186f. It's a potential Earth-like planet, just 10% larger than Earth. This planet orbits a red dwarf star, which is a star a bit dimmer, colder, but more long-living than our Sun. And it's only about 490 light-years away, which may sound like a lot, but remember what distances we've discussed with supervoids. So, even if we really are in a supervoid, we're still lucky to have many galaxies and planets around. And if one day we'll find a way to travel through the universe, leaving the local hole probably wouldn't be a problem. A long time ago, we believed that the entire universe revolved around our own little blue planet. It's called a geocentric model. We thought that the sun, the stars, and all those twinkling celestial bodies all danced around us. This theory was super popular in ancient Greece and Rome. Famous geniuses like Aristotle and Ptolemy really loved this idea. Why did people believe this in the first place? Well, first of all, we have a massive ego. Second of all, there were a couple of things that seemed to support it. For example, if you stand on Earth and look up at the sun, it seems like the sun is spinning around us once every day. The moon and the planets seem to be doing the same thing. The obvious conclusion is, oh, they're probably twirling around the Earth. It's just on 3-sec pause. Then there's the fact that Earth feels pretty steady when you're standing on it. It just doesn't feel like it's moving, you know? And because of this stability beneath our feet, people thought that the Earth was unmoving. But even back then, there were ancient Greek and Roman philosophers that were onto something cooler. They paired the geocentric model with the idea that Earth was actually a round ball floating in space, not a flat disk. They started connecting the dots, and after a while, astronomer and mathematician Aristarchus of Samos had a game-changing idea. He thought that the Earth might not be the center of everything. He proposed that everything revolved around the sun. Funny to think that back in the days, this idea was considered insane. 2. 3-sec pause. That's why for a while, most people stuck to their geocentric views. It took us many centuries to finally accept the heliocentric model, where all the planets in our solar system revolve around the sun. This idea was brought to life by people like Copernicus, Galileo, and Kepler. This change wasn't easy for people. It was hard to let go of our space crown, but gradually we came to terms with it. And by letting go of this idea, we discovered a whole new world. This journey led us to an astonishing realization. Not only we're not the center of the universe, we're nothing but a little speck in it. We're a microscopic dot, sprawling galaxy called the Milky Way. The discovery of the Milky Way started right from our own backyards. If you've ever gazed up at the stars on a clear night, you might have noticed a faint, luminescent band stretching. It's like a shimmering celestial ribbon woven with stars. That is our galaxy. It was named Milky Way because it looks like someone spilled milk on a road. 3-sec pause. It was perfectly depicted in the 90s by Voyager 1. NASA's spacecraft took a picture called the pale blue dot. That tiny little pixel that's almost impossible to see is our planet. The photo was taken from a chilling 5.96 billion kilometers away from the sun. On a universe scale, this distance is nothing. But for us, it's unimaginable. So when scientists discovered the Milky Way, they armed themselves with telescopes. Their goal was to map the uncharted territories of the night sky, and, of course, to find our place in this gigantic world. To do that, first, we had to unlock the secrets of our galaxy's structure. Okay, so we can clearly see that it has some band-like formation. That probably means that our galaxy is not a big, round ball like the planets and stars. In reality, it's more like a giant pancake, a flattened disk. And we can see that we're not above it and not below it. We're right on the plate. Software 3-sec pause. The next step is to travel across the Milky Way to map it. There's a little problem though. To do that, we'd have to traverse thousands of light years perpendicular to this pancake-like plane. Just to put things in perspective, think of Voyager 1, the one that took the pale blue dot picture. That spacecraft has been journeying through space for almost half a century. It left the solar system years ago. You know how many light years it traveled? 0.002. And how many light years is the Milky Way? 100,000. You get the picture. But the lack of fancy technology didn't stop us. In the 18th century, a bold astronomer named William Herschel decided to explore our galaxy. With nothing but a telescope, this Indiana Jones of astronomy started mapping the stars in the night sky. As a result, he discovered Uranus, more than 2,000 nebulas, and created the first map of the Milky Way that depicted it as a disk. The map wasn't super accurate, but still very impressive. 3-sec pause. Unfortunately, he didn't know about something called interstellar dust. It's like space fog that can block our view of stars in the center of the Milky Way. This dust made the central region of the Milky Way appear less crowded than it actually is. Now, let's go all the way to the 20th century. Henrietta Swan Leavitt, an American astronomer, was another curious stargazer, but she focused her attention on a special kind of star called Cepheid variables. These stars had a unique quirk. They pulsed, getting brighter and dimmer in a predictable pattern. Leavitt's job at the observatory was like being a librarian. She cataloged these special stars, and in doing so, she stumbled upon something incredible: a direct link between the brightness of these stars and the rate of their pulsations. This discovery is now known as Leavitt's Law. It meant that by simply measuring how quickly these stars pulsed, astronomers could figure out how far away they were. These pulsating stars became the rulers for measuring distances. 6 3 sec pause. 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 6 3 Before the 1920s, most scientists believed that our Milky Way was the only galaxy in the universe. But as telescopes improved, some astronomers started realizing that this isn't the case. We started finding more and more galaxies. But if the Milky Way was just one of many galaxies, where exactly were we within it? Meet the scientist named Harlow Shapley. Armed with a powerful telescope, Shapley turned his attention to globular clusters. These are tightly packed groups of ancient stars that gather together in spherical shapes. That's when he noticed something interesting. The oldest stars around us weren't scattered all over the canvas. They were clustered around the center of the Milky Way, and they were pointing in the direction of certain constellations like Sagittarius and Scorpius. Slot 3 sec pause. It turns out that the origin of our galaxy began from the center. It was the heart of the Milky Way, and the most ancient guys were hanging out there. Which means we're not even at the center of our own galaxy. Seems like our importance becomes less and less with each new discovery, huh? Anyway, Shapley found out that we were positioned somewhere on the outskirts of our galaxy. Shapley's calculations weren't perfectly accurate, but he got pretty close. Luckily, now we have very precise and cool tools. Since then, we've since pinpointed our precise location. We're located near a partial arm of the Milky Way called the Orion Arm. It's about 26,000 light years from the heart of our galaxy. And that was the story of how we found out where we are in the Milky Way. After sec pause. You think our story is over? Oh, absolutely not. Meet Gaia, the European Space Agency's celestial cartographer. Launched in 2013, Gaia embarked on a daring mission. It has to map the Milky Way in unprecedented detail, not just some rough map, but a photographer capturing every nuance of our galaxy. Gaia is piecing together the positions and motions of about 1 billion stars. And it's like 1% of the stars in the Milky Way. But even that tiny fraction is enough to create a masterpiece of cosmic cartography. What a grand journey it was. It led us from thinking Earth was the center of the universe to realizing we're less than a speck in the grand scheme of things. But what's more important is that this story shows humanity's drive to uncover the mysteries of the world. And there's always something new to explore. Discoveries just keep coming, so stay tuned and keep looking at the night sky. Could it be that the entire universe is nothing more than just an atom? When you look at a diagram of an atom, which is a building block for all matter, you can see that some patterns in the universe repeat. Our solar system is a great example of that. There's a giant central star and a couple of smaller planets that circle around it. You observe the same arrangement outside of our galaxy too, with exoplanets orbiting their stars. And you can also witness that principle on a smaller scale. It's the way particles called protons and neutrons move around the center of an atom, which is called the nucleus. So, imagine you have a bunch of positive magnets you're trying to stack together. They keep pushing each other away, right? That's what's supposed to be happening with the protons in an atom. They're all positively charged, so they should be repelling each other and flying off in all directions. But atoms do exist, so there must be something holding them together, and that something is called the strong interaction or strong force. The nucleus makes up less than 0.01% of the volume of the whole atom, but it usually takes up over 99.9% of the mass of the atom, once again similar to our sun. Anyway, this strong interaction is like a special type of glue that holds the protons and neutrons together in the nucleus of an atom. In a similar way, gravity prevents us from flying away from the ground into the darkness of space. Now, this glue comes from some really small particles inside protons and neutrons called quarks. These little guys have a strange kind of charge called color. It's not like the colors we see around us. It works like a code that helps quarks stick together inside their host particles. And this code also seeps out and helps hold protons and neutrons together in the nucleus. In a way, quarks are like little builders that are working together to build atoms that make up everything around us. The Big Bang was said to be a magnificent moment when we got time and space. It's the story we use to explain the evolution of the universe. In the beginning, there was only a very, very small ball of matter the size of a peach, but with a temperature of more than a quadrillion degrees. Ow, that's hot. And this bang in the name doesn't mean there really was an explosion in space. This peach started spreading around, and space was just appearing everywhere. It gave rise to atoms, molecules, stars, and many celestial bodies that filled the empty space of our cosmos. Basically, all the elements that make us formed within a few minutes at the earliest stages of the universe. Let's say, like 100th of a billionth of a trillionth of a trillionth of a second. Oh wait, give me a second to process that. Alright, moving on. The growth was incredible at that stage. The universe spread exponentially, and managed to double in size at least 90 times. Like me during the holidays. Haha, I love chocolate. After the Big Bang, the universe was a hot and dense soup of particles, too hot for atoms to exist. But 380,000 years later, it cooled down enough for electrons to mix with nuclei and form atoms. This is a process we call recombination, and it's what made the universe transparent. Think of it like turning on a light switch. Suddenly you can see it all. But just because the universe became transparent didn't mean it was bright. It was a dark period as there were no stars or galaxies yet, like a big empty canvas waiting for something to be painted on it. It wasn't until much later, as the universe continued to evolve, that stars and other bright objects started to form and light up the darkness, and it went on evolving, all the while filling up with planets, asteroids, galaxies, and other things. Okay, so that's the story we've been told for the past couple of decades, and a pretty good one, I should admit. Scientists have studied it so much. They observed the leftover electromagnetic radiation from the young universe. They measured the presence of the lightest elements, only to realize they all line up with the story of the Big Bang. New theories don't say the Big Bang didn't happen. It's a good picture of the cosmos in its early stages, but it's like an unfinished puzzle with some important parts missing. We can't explain what happened before the Big Bang using our current physics, so we need some new math to explain tricky parts, like the so-called singularity. It's the point of infinite density, remember? From the beginning of the Big Bang. And that's where string theory comes in. Like a superpowered toolkit that can handle gravity and all other forces combined. Now, one of the ideas that string theory has given us is the ekpyrotic universe. Imagine a big fire that sparks off another fire, and that fire sparks off another fire, and so on. Well, in this scenario, the Big Bang wasn't the beginning of everything. It was just one part of a bigger process. It's the idea of the cyclic universe, a never-ending roller coaster ride, with big bangs as beginnings and big crunches as ends, happening over and over again, potentially forever. It's like the universe is constantly hitting the reset button, and does it in a really fun way. We could look at this singularity, according to some theories, as a single particle in a much larger system, much like an atom is made up of subatomic particles. And considering all that, the idea says every nucleus of an atom could have a universe inside of it. So our entire universe is just a tiny part of an atom in a much larger universe made of atoms with more cosmoses, with more atoms, with more cosmoses. So twisted. The early versions of the idea of the cyclic universe still had one big issue. They didn't match up with our observations of the cosmic microwave background, which is a fossil light that shows how the universe looked when it was only 380,000 years old. So, in March 2020, two physicists from Canada, Robert Brandenberger, Ziwei Wang, published a study that revealed the math behind the cyclic universe that we had missed earlier. If we focus on the moment when the universe shrinks to an incredibly small point and then bounces back to a Big Bang state, we might be able to match up with our observations after all. It's just that we need to wait for more new experiments to fully test this idea. The Grand Unified Epoch. That's what we call the time when the universe was still young. At that time, matter and antimatter, which are like mirror images of each other, existed in roughly equal amounts. But since they are opposing forces, when they come into contact with each other, they destroy each other in a powerful explosion, like fireworks. This means that even though matter and antimatter were constantly created and destroyed, somehow there was always a little more matter than antimatter, which is good, cause otherwise we wouldn't have anything left. As time went on, particles started to stick together and form more complex things like atoms and molecules. And eventually, stars formed and created even heavier elements. But someday, a long time from now, all those stars will burn out. When the last star slowly cools and fades away, the universe will turn into a dark void without life, light, or anything we know or assume there is. At some point, voracious black holes will eat all the matter in space. Eventually, even those black holes will evaporate away into the tiniest amount of light. Our cosmos will continue to expand. The light will become spread out and unable to interact with anything. So all activity in the universe will stop. Space will become a vast, empty void with no stars, planets, or anything else, and will end there. Or just begin, and maybe that's where we'll meet again. Well, my cosmic pal, do you ever feel like everything is just drifting apart? Well, your intuition may be right. It turns out something weird is indeed happening in the universe. Since the Big Bang, everything has been spreading out in every direction and getting faster every day. But here's the thing, not all galaxies are moving at the same speed. We have some seriously massive clumps of matter out there that are slowing us down. And there's one giant, mysterious gravitational anomaly that's been dubbed the Great Attractor. No, we're not counting me, though we share the same nickname. It's the mystery of mysteries, and it's been pulling us and all the nearby galaxies closer to it for billions of years. Scientists aren't certain what this Great Attractor is made of, but it's so powerful that it overcomes dark energy, which makes up about 2/3 of the universe. Dark energy is more or less like the universe's energy drink, pushing everything forward and giving galaxies a boost in their movement. So where is this thing? Hiding in the zone of avoidance, which sounds like a made-up town from a sci-fi movie, but is actually a real place in the universe. There's just so much stuff between us and the Great Attractor, stars, gas, dust, that we can't even see it. Some astronomers think this is just how the universe ends. Everything clumps together into one giant supercluster, and then boom, big crunch. It's like when you're trying to fit all your clothes into one suitcase, and it just ends up exploding everywhere. Now, before you start thinking that galaxies moving is no big deal, let me tell you that this isn't just any ordinary movement. You see, this thing called the Hubble flow dictates that galaxies should be receding from one another as the universe expands. But, as luck would have it, that's not what's happening. The Great Attractor is so strong that it even affects our own galaxy, hurtling us toward it at more than 1,000,000 miles per hour. I'll spare you the math, but if we spun around the sun at that kind of speed, our year would be a mere 18 days long. The Great Attractor was first noticed in the 70s, but our technology wasn't quite up to the task of seeing through the zone of avoidance. Nevertheless, X-ray technology has come to our rescue in recent years, and it has helped us piece together some of these hidden parts of the universe. What can this Great Attractor be, you might ask? We can only make assumptions at this point. The most likely solution is that it's a galactic cluster. They are basically the universe's version of a massive family reunion. These bad boys are held together by their own gravity and can pack hundreds, or even thousands, of galaxies, along with a ton of hot plasma and sneaky invisible dark matter. Ooh, see. The X-ray data have revealed a plethora of distant galaxies that we previously didn't know existed. Not only that, but 2 new galaxy clusters have been found the Norma Cluster and Shapley Supercluster. The Norma Cluster has a mass of roughly 1,000 trillion suns and comprises thousands of galaxies. It's possible that the Norma Cluster is the reason for the Milky Way's high-speed hurtle through space, but it still can't explain the movement of thousands of galaxies around us. However, when scientists peered deeper through the zone of avoidance, they spotted the Shapley Supercluster. This behemoth of a galaxy cluster is the largest within 1 billion light years. It could explain the movement of galaxies in our sliver of the universe. More than 8,000 galaxies create a mass of more than 10 million billion suns. Most scientists have accepted that the Shapley Supercluster is most likely the force behind the Great Attractor. It lies in the region where the pole appears to be coming from, and logically, it seems to make the most sense. There's more though. Some researchers take pause at the proximity of the Shapley Supercluster to other clusters. Too many galaxies come together in various clusters there, openly defying the Hubble flow. Some experts believe that a large gravitational anomaly is a real answer to the Great Attractor. There have been theories ranging from a supermassive black hole, larger than anything we could possibly imagine, to some sort of life form making a mess in that corner of the universe. The Great Attractor is not the only weird thing we've stumbled upon in the universe, as you can imagine. Have you heard of the Red Rectangle? No, it's not a new dance move, but an amazing nebula surrounding a star called HD 44179. This star is a lot like our sun, but it's at the end of its life, and is spewing out gas and other materials to create this incredible structure. Some scientists think that the star might actually be a close binary, meaning it has a partner, and that there's a thick ring of dust around it. And even though we've got some ideas about how the Red Rectangle got its shape, scientists are not entirely sure. One thing we do know for sure is that the Red Rectangle is a type of nebula called a protoplanetary nebula. And when that happens, there will be a super hot white dwarf star left over, which will give off some seriously cool ultraviolet radiation and make the surrounding gas glow. As for its location, it's about 2,300 light years away, hanging out in the constellation dubbed the Unicorn. Not all weird space objects are so far away from us in the universe. Some of them may be lurking pretty close to home. In January 2015, two clever astronomers made a prediction that a gigantic planet could be spying on us from our outer solar system. Now, before you start getting too excited, we should point out that they haven't actually seen this mammoth world yet. Their prediction is based on some pretty basic math and computer simulations, so there's still some debate about whether this prediction is true or not. But if it is, this planet, which scientists have nicknamed Planet 9, also called Planet X in the past, could be up to 10 times the mass of our own Earth and about the same size as Uranus or Neptune. What's really unusual about this mysterious planet is that its predicted orbit is extremely elongated, making it unlike any other planet we've seen before. In fact, it's estimated to be about 20 times further from the Sun than Neptune, and it takes between 10,000 and 20,000 years to complete just one full orbit. You might be asking yourself, how can anyone predict a planet they've never seen before? Well, these scientists noticed that at least 5 other smaller objects floating around in the distant parts of our solar system seem to be following similarly unusual orbits. By analyzing these orbits, astronomers worked out that there must be a big, undiscovered planet out there causing all the fuss. To figure out this mystery, astronomers will be peering into the universe's most powerful telescopes to see if they can spot this elusive Planet 9. However, it won't be an easy task, since an object that is so far from the Sun must be very faint and difficult to detect. Some astronauts have even experienced the Bermuda Triangle equivalent of space while passing through the South Atlantic anomaly. This is a region in Earth's magnetic field where 2 rings of charged particles come closest to our planet's surface. And as luck would have it, this area happens to be high above the South Atlantic. computers can go haywire there, and astronauts can see cosmic flashes, possibly because of radiation stimulating their retinas. And it's not just poor astronauts who have to deal with this anomaly. Even the Hubble Space Telescope is unable to make observations when passing through this region. It's a real pain in the telescope's lens. So, what's the deal with this SAA? It turns out that our planet's magnetic field is not perfectly aligned to its rotation axis, which causes the two particle rings to tilt. And as a result, we end up with this region that's causing all sorts of trouble. Well, space is just one thing or another, isn't it?